Assalamualaikum warahmatullahi wabarakatuh everyone. We are here today to present a topic that demonstrates how mathematics is applied in our daily lives. The title of our presentation for MAT210, Application of Logic in Real Life, is Traffic Light. This presentation is specially prepared for our lecturer, Madam Suzana Aida Othman, to showcase how logic is used in something as common yet essential as traffic light. Let's dive into how logic makes our road safer and traffic flow smoother. Now, let us introduce the members of our group. On the left, we have ATHIRAH AYUNI binti ROZALI with the metric number 202269148. And on the right side, we have ATHILAH NABILAH binti ZULKEFLI with the metric number 202261382. Together, we worked on this project and we're excited to share it with you. Let's move on. Introduction. Effective traffic management is vital for efficiency in transportation, with logic playing a key role in controlling traffic light. This project examines the connection between mathematical principles and traffic control decision, focusing on how logic impacts movement at intersections. It aims to demonstrate how mathematical ideas can optimize traffic flow and enhance city mobility through practical application.
Let's continue with description. Statement. A statement or a proposition is a declarative sentence that is either true or false and not both. Statement normally represented using verbs like P, Q, R, S. Moving forward with truth table. Use T for true and F for false. Truth table normally used in logic, computer science, and mathematics to analyze the behavior of logical expression and circuit. The truth table of two variables have four rows: 2 true, 2 false, 1 true, 1 false. And then for the truth table of three variables will have 8 rows: 4 true, 4 false, 2 true, 2 false, 1 true, 1 false. Next, logical connective. First, conjunction. Conjunction of statement P and Q is denoted by PQ and is read as P and Q. If any of P or Q is false, then P or Q is false. If both P and Q is true, then P and Q is true. This is the truth table of conjunction. And next, disjunction. Disjunction of statement P and Q is denoted by P or Q and it's read as P or Q. If any of P or Q is true, then P or Q is true. If both P and Q is false, then P or Q is false. Okay, this is the truth table of disjunction.
Negation and implication. Let's start with negation. Negation is used to give the opposite true value of a given statement. If a statement is true, its negation is false, and vice versa. The negation of a statement P is denoted by not P, and we read is at not P. Here the truth table for negation. When P is true, not P is false. When P is false, not P is true. So, negation is essentially flipping the truth value of the original statement. Now, let's move on to implication. Implication connects two statements P and Q and is denoted by P implies Q. We read this as if P then Q. In simpler terms, it expresses a conditional relationship between P and Q. The truth table for implication is as follows. If P is true and Q is true, then P implies Q is true. If P is true and Q is false, then P implies Q is false. If P is false, P implies Q is true, regardless of Q truth table. The key point to remember here is that the implication is false only when the first statement P is true and the second statement Q is false. Biconditional. A biconditional is a logical statement that combines two propositions P and Q. It is denoted as P biconditional Q and is read as P if and only if Q. The biconditional means that P and Q must either both be true or both be false for P biconditional Q to be true. If P and Q have different true value, then P biconditional Q is false. Let's look at the truth table for P biconditional Q. When both P and Q are true, P biconditional Q is true. When P is true and Q is false, P biconditional Q is false. When P is false and Q is true, P biconditional Q is false. When both P and Q are false, P biconditional Q is true. The key point to remember here is that a biconditional statement holds true only when P and Q have the same true value. In simpler terms, it checks for logical equivalence between the two statements.
First of all, we will start with example 1. You can see the picture we provide there. Okay, in a four-way intersection, if the east direction has a green light and the west direction has a green light, then the north direction should have a red light and the south direction should have a red light. Proceed with logical statement. If the east direction has a green light, we can denote as P. Or the west direction has a green light, we can denote as Q. Then the north direction should have a red light, we can denote by R. And the south direction should have a red light, we can denote by S. Okay, after the logical statement, we can break the statement into small parts. Like I said just now, P, the east direction has a green light. Q, the west direction has a green light. R, the north direction should have a red light. S, the south direction should have a red light. Okay, now let's move to the logical expression. We make this like P or Q implies by R and S. Okay, let's move to the truth table. First, P or Q. If any of P or Q is true, then P or Q is true. If both P and Q is false, then P or Q is false. Okay, next, R and S. If both R and S is true, then R and S is true. If any of R or S is false, then R and S is false. Okay, next, for the P or Q implies R and S. If P or Q is true and R and S is false, then P or Q implies R and S is false. Otherwise, P or Q implies R and S is true. Okay, from the table we can define that the statements are contingency because the 7 column contain both true and false. Continue with logical circuit. After that, we need to simplify the expression. We use law. First one, we use definition of implication. Second, we use De Morgan law. And as you can see, the picture is the logical circuit. And the simplified expression is not P and not Q, or R and S.
Let's move on to example 2. If the traffic light is green, then they can proceed through the intersection. If they can proceed through the intersection, then they can reach their destination. The traffic light is green and they can proceed through the intersection. Therefore, they can reach their destination. Next, I will be explaining a logical statement. This example consists of 3 logical statements represented as P, Q, and R, and demonstrates how we can deduce conclusion using logic. Statement 1. If the traffic light is green, P, then they can proceed through the intersection, Q. This is a conditional statement where P implies Q. It means that the green light is a necessary condition for proceeding through the intersection. Statement 2. If they can proceed through the intersection, then they can reach their destination. This is another conditional statement where Q implies R. It means proceeding through the intersection ensure they can reach their destination. Statement 3. The traffic light is green and they can proceed through the intersection. This combines P and Q using a conjunction P and Q. It confirms both events are true. I will walk you through a logical reasoning process, breaking a situation into smaller parts and representing it as logical expressions. First, let's define the scenario. P. The traffic light is green. Q. They can proceed through the intersection. And the last one is R. They can reach their destination. By breaking this into smaller parts, we can understand the relationship between the different statements. Next, we express this relationship using logic. Number 1. P implies Q. If the traffic light is green, they can proceed through the intersection. Number 2. Q implies R. If they can proceed through the intersection, they will reach their destination. Number 3. P and Q. This represents the condition where the light is green and they proceed through the intersection simultaneously. Number 4. R. This is the ultimate result. They can reach their destination. By breaking statements into smaller parts and representing them as a logical expression, we can clearly understand the cause and effect relationship within a scenario. This approach is very useful for problem solving and reasoning. Now, let's look at how we can prove that an argument is valid. Logical reasoning helps us verify the validity of an argument step by step. This is what we will explore in the following table. Here is the structure of our proof. Number 1. P implies Q as premise 1. Number 2. Q implies R as premise 2. Number 3. P and Q as premise 3. From these premises, we begin to draw a logical conclusion. Let's follow the step in the table. Number 4. By using syllogism with premises 1 and 2, it will be P implies R. Number 5. By using simplification with premise 3, it will be P. Number 6. Finally, by using modus ponens with step 4 and 5, it will be R. This step-by-step reasoning confirms that the argument is valid. By following logical rules like syllogism, simplification, and modus ponens, we ensure a sound and clear reasoning process. Let's dive into the concept of a logical circuit. A logical circuit visually represents logical relationships and processes using standard logic gates. This can help us better understand the flow of logical reasoning. In this circuit, we start by translating logical expressions into their equivalent forms. Number 1. P implies Q is equivalent to not P or Q. Number 2. Q implies R is equivalent to not Q or R. And the final one is condition P and Q will just stay the same. This expression from the basic of the logical circuit. The logical circuit is represented as follows. The first block evaluates not P or Q. The second block evaluates not Q or R. The third block evaluates P and Q. The output of these logic gates flow together, leading to the conclusion R, which represents the final result of the logical circuit.
And finally, the presentation comes to the end. Last but not least, conclusion. Logical reasoning is crucial in designing city traffic light system, optimizing timings for safety and flow, adapting to dynamic conditions, and prioritizing transportation needs are key challenges. Coordinating multiple lights at intersections reduce congestion and improve city mobility. I think that's all from us. We have covered everything we wanted to share. That's all we have today. See you for the next presentation. Thank you for watching. Bye.